our modeling, even without control, with control as well, we're getting ordinary differential equations, mostly either linear or nonlinear. When they're nonlinear, we're linearizing. So we're manipulating them into a linear form. And then we want to solve them. And we saw that using the standard methods of ordinary differential equations is perfectly doable, but it involves lots and lots of writing. And the more we write, the more likely we are to make mistakes and to get lost in the algebra. So we said there's another method called Laplace transforms, which turn derivatives and integrals into algebraic equations, just into algebra. By the way, I'm going to continue taking attendance because, at least in the class, because I'll bet there's a correlation of the people who miss a lot of classes with the people who never learn the material. As I said in my email, I'm often not fussy about attendance if people are doing well in the class. If someone does well in the exams, frankly, if they don't come to class, it's okay, because they obviously learn the material. That doesn't work if people are not doing well in the class. If people are not doing well in the class, then they have no excuse if they don't come to class, and that's probably a good reason why they're not doing well in the class. Okay, in any case, it turns derivatives and integrals into algebraic forms, and then we can solve for the Laplace transform of the variable of interest from an algebraic equation, much easier. But then we have to get the full solution, we have to integrate back. And we integrate back using these tables that give me f of t and f tilde of s next to each other. And what we said is, instead of having infinitely long tables, whenever we have a function that's f tilde of s, the first thing we do is we break it up into a sum of the simplest possible functions I can break it up into. And that's called partial fractions. So we spent some time doing partial fractions in 3 different cases. We were always looking at cases where where f tilde of s is a numerator or a denominator, where both of them are polynomials. And if they're polynomials, then I can factor the denominator into s minus alpha 1, s minus alpha 2, etc. And then we show that we can break that up. If all the alphas are different, then we can break it up into a sum of terms that look like, each term looks like something over s minus alpha. And when we invert that, we just get e to the alpha t. If there are multiple, if we have some of the alphas the same, then we can again break it up, and we showed how, but we'll get terms in the inverse that look like t to a power e to the alpha t. Not just e to the alpha t, but t to a power e to the alpha t. And finally, if the alphas are complex, if we have complex conjugate alphas, then when we do the inverse, we'll have e to the alpha t times sine omega t. A constant times sine is a constant times cosine. Where if the root is alpha plus or minus I omega, we have e to the alpha t times a sine omega t plus b cosine omega t. So we have something that oscillates times something that either grows or decays. So we said that, and we noted that if we had multiple roots, if we had the complex roots appeared more than once, the same complex roots, then we would expect t to a power times e to the alpha t times the cosine of the sine. So those are, now, it's nice to be able to do inverses. We can look them all up. But one theme of today's lecture, and last time's lecture, probably the next lecture, is that, inverting Laplace transform might be a pain in the butt. And it gives us a lot of information, much of what we may not need. So do we really need to know? Do we really absolutely need to know? We might want to, but do we really absolutely need to know the value, let's say if I have a reactor of Ca, or of the pressure, or of the temperature in the house, do we need to know the value at every instant in time? Or are we just interested in certain, is it going to blow up or not? Is it going to oscillate or not? And we will, as we will see probably next lecture, I probably won't get to it today, we saw typical disturbances. We could have step disturbances, we could have delta disturbances, but you might also have a sinusoidal disturbance. Why might you have a sinusoidal disturbance? Let's say you have a chemical plant out in the open in New Jersey. Not exactly fiction, there are a lot of them. You have an oscillatory temperature between day and night. It oscillates. You want to know, do I really have to put tons of insulation on everything, or is it not a problem? What happens if I have this oscillatory input of the temperature between day and night? What's the result? How does that affect what's going on? And as we'll see probably next class, but maybe I'll get to the beginning of that this class, that you can determine whether things are going to blow up, whether things are going to oscillate. What is the response to a sinusoidal input? You can determine those things directly from the Laplace transform without inverting. So you take a hard problem with derivatives and integrals, you transform it into an algebraic problem that you can solve, and then you might be afraid of having to do the inverse. But most of the time, you don't even have to bother. You can get all the information you need just from the Laplace transform. Because you have a final value theorem. Because you have, once you do the partial fractions, you can evaluate just by factoring the denominator. Just by finding the zeros in the denominator and looking at them, you know all the issues of stability, which I had on the blackboard at the end of the last hour. And as you see, you'll also know the frequency response. So that's sort of the goal here of what we're doing. And if you remember, at the end of the last hour, I just wanted to point out I made a slight error in the last second of the class. I had defined at the end of the hour what a transfer function was. And we said the transfer function was the Laplace transform of the output over the Laplace transform of the input. Now, if I have many outputs and many inputs, I have lots of transfer functions. So I have a transfer function for each combination of output and input. The main thing is it's where the input with the initial condition is 0. So that means I'm always dealing with prime variables where the initial condition is 0. So we looked at a particular problem. We looked at the problem of a CSVR where I have a step change in t equals 0 of Ca in and of the volumetric flow rate, where they both happen to t is equal to 0. And I went through and I came up with this equation. And and then I Laplace transformed it and got this equation. But if we looked at this equation, so if we look at it, here's the Laplace transform. And notice this is the output, Ca prime tilde, and there were two inputs that were changing, V prime and Ca in prime, because both of them changed to t is equal to 0. So that tells me, remember, I have a transfer function, and these are all prime variables. So that tells me I have one output and two inputs. So that means I have two combinations of output input. This guy and this guy, or this guy and this guy. So I've got two transfer functions. And I wrote them out. The transfer function of this guy and this guy says set all of the other inputs to 0, and it's the ratio of this guy over this guy, so just this. So G for Ca prime tilde V prime tilde is just this, which was this quantity. Okay, and similarly, G for this guy and this guy is just this. And I made a little error there, is that Remember, I have the t0 over 1 plus st0, this thing times this. Okay, there's no error here. But in the transfer function of this, with respect to this, I have v over little v over big V, times t0 over 1 plus st0. And I mistakenly identified this as t0. This is tau, not t. So this is tau 0, 1 over tau 0. And t0 is tau 0 over 1 plus k tau 0. So if I to write this correctly, let's just do the steps now. T0 is tau 0 over 1 plus k tau 0. So when I plug in here, I divide by tau 0, that cancels the tau 0. And what I'm left with is 1 over 1 plus k tau 0 times 1 over 1 plus st0. So that's what this transfer function is. Questions? So that's just fixing the error from last time. What happens when I try to write just one more equation as the hour is over? Questions? Okay, we'll be working with these guys a lot, transfer functions. You'll see they're quite useful. But first, I want to start the new part of today's lecture with some terminology. Again, I'm going to erase this, but here you can see the bell curve where the mean of the bell curve is way too low. It should have been up here. Usually they say when you get a bell curve, it means it was a good exam. But I think they mean that's when the mean is a little higher than this bell curve. Okay, a little terminology. And this refers to what do we transfer function. So the first thing is, what's the order of a transfer function? The order is the highest derivative of the output variable. Actually, before I can say that, I want to point something else out here. As we said, when we write out the equation here, the left-hand side is the system without disturbances. This only depends on the system, no disturbances. And notice that the time constant depends on the system, not on the disturbances. Remember, this is the Ca prime dt plus a constant times Ca prime. That's all, and the constant, k plus 1 over tau 0, is the time constant of the system. Has nothing to do with the disturbances. It's the natural part of the system. The disturbances are on the right. So the left is the system, the right is the disturbances. Remember, we are talking about Laplace transforms, or if you like, we're going to be talking about transfer function. When we take the Laplace transform of the left side, we took the Laplace transform of the left side. We had s plus 1 over t0. So notice this thing, the left-hand side, was Ca prime tilde times 1 plus st0 over t0. So this thing is a polynomial in S. It's just a linear polynomial, but it's a polynomial in S. And the polynomial in S that comes from the left side, that comes from the system without disturbances, is called the characteristic polynomial. It's called the characteristic polynomial because it's characteristic of the system and not of the disturbance. For any disturbance, I always have the same characteristic polynomial. And notice that when I write out Ca prime tilde, It's the characteristic polynomial that goes in the denominator. So the left side of the equation is the system, the right side of the disturbances. The Laplace transform of the left side gives me the characteristic polynomial. When I solve for CA prime, which is in the numerator of the transfer function, I get in the denominator of CA prime is the characteristic polynomial. And it's the denominator whose roots we look at to get the stability. So maybe I should write that out. So here's the logic. When we do a problem, the left-hand side is the system. The Laplace transform of the left-hand side gives me the characteristic polynomial. When I solve for the output, prime tilde, I get some sort of numerator divided by the characteristic polynomial. And as we saw, it's that denominator that gives me stability, information. Because that's the thing I factor. And then that's the thing I factor, and I do my partial fractions based on that. The important thing is all the stability information is coming from the system, not from the stability characteristics come from the system, not the disturbances. The disturbances drive it. But notice, when I have my transfer function, it's the output prime tilde over the input prime tilde. The output, we said, is this guy, output prime tilde. It's got some numerator over the characteristic polynomial. When I go to this g tilde of s, this has got the output prime tilde over the input prime tilde. Well, that's going to be, again, I have the numerator over some characteristic polynomial. And what is the input prime tilde? Well, the input prime tilde, this guy, or this guy, those are, if they're delta inputs, it's just a constant. And if they're step functions, it's just s times a constant. It's just s times a constant, or 1 over s, whatever. So I just have this extra factor of s. So at worst, I just have this extra factor of s. But most of what's in the denominator that's telling me the stability is the characteristic polynomial. I'm sorry, with the mask, I'm not.
Yeah, sorry. Is it the same characteristic polynomial as in the output filter?
Yes, yes. I just copied it from here. That's why, because I have the output here. So I recopied it here. So then I may have some contribution from input. But that contribution is at worst a factor of s. I think it's 1 over s. I think of the step function. Yeah, it's 1 over s. So that would go in the numerator anyway, since it's a 1 over s. So the contribution from the input is either a constant or sticking another s in the numerator. So that's not particularly, it doesn't affect the denominator. So that's telling you that the stability characteristics are from the characteristic polynomial, which are from the system and not the disturbances. Okay, so with that in mind, So the order of G of S is the highest power of S in its denominator. In denominator of G tilde. Well, now why do I care about that? We know we care about that because that's telling me how many factors I have in the denominator. And when I do my partial fractions, I need to know how many roots to look for. The poles of G tilde of S are just the zeros of the denominator. So that's just the word for the zeros of the denominator, are the poles of G. Why they call them poles, I don't know. Nothing to do with Poland, which I have to say since my last name is Polish. Okay, zeros. Zeros, is that it? Yeah, this is another word for the same thing. Zeros are called zeros of G tilde of S are the roots of the numerator of G tilde of S. So that's just a little bit of terminology. And I'm going to erase this and this will be more one.
Is there a reason you use zeros in one line and roots in the other line? To me, they're the same.
Yeah, because zeros, remember, it's the zeros of what? This is zeros of G tilde. The zero of G tilde is when G tilde is 0. So it refers to the numerator. The order is the the poles are when the denominator is 0. So that's why I didn't underline 0 here, I underlined it here. So when I'm referring to the denominator of G tilde, I say pole. When I'm referring to the numerator of G tilde, I say zeros of G tilde.
Okay.
I need a different word for what's going on in the numerator from what's going on in the denominator.
But in either case, if you factor it and one of the terms is 0, that's your
I'm
0
sorry?
or your root, depending on whether you're talking about the numerator or
Yeah, that's right. It's just terminology for the numerator and terminology for the denominator. It's the same idea, but the zeros, the poles of G are much more important for stability than the zeros of G, as we'll see right now. Well, if you recall, when we did partial fractions, this chalk is getting too small. Okay. When we had, we typically had n tilde of S over d tilde of S, numerator over denominator, was equal to, let's say when the roots were distinct roots. We had m1 tilde of alpha over S minus alpha plus something else. So we had terms that looked like this. And what was m1 tilde of alpha? m1 tilde of alpha, m1 tilde was equal to n tilde of s divided by, not d tilde, but either d tilde of s divided by s minus alpha. So it was all the factors of d tilde except s minus alpha. Or we also noted it was equal to n tilde of s divided by d tilde ds at s is equal to alpha. So there's one or the other. This is at s equal alpha. This is, you have this in your notes, right? So I want you to notice that the stability only depended on this because, recall, 1 over s minus alpha, if this is f tilde of s, corresponds to f of t is e to the alpha t. And we found similar things for multiple roots and for complex roots. We had a bunch of terms where it was the denominator that was calling the shots. So notice, and the only thing that the numerator does, n and all the other factors of d, but the other factors of d come in other terms. So really all the other factors in d are important because they come into the denominator of the other terms that look like this. But the numerator part is just a bystander. It's not doing anything interesting. The numerator is just contributing to m1 tilde of alpha. What is m1 tilde of alpha? m1 tilde, when I invert this, I'm going to get an m1 tilde of alpha times e to the alpha t. So the numerator is zeros of this. These just contribute to the coefficients. Only contribute to coefficients. The actual time dependence, the actual stability, comes from here. Because the numerator, and the numerator, remember, well, it came from, the numerator came, well, here, this is the numerator here. The numerator from the output and whatever contribution there is from the input. And notice there is a contribution from the input when I have a step change, because that gives me an s in the numerator. The numerator is less important. It contributes to the coefficients, which are the detailed time dependence of the solution. But it doesn't contribute to the stability. The stability all comes from the denominator. So let's just notice again from that. Remember, g tilde of s is the output. I'm going to call y prime tilde the output. This one output. Over x prime tilde as input. So I want to establish that notation so I don't have to keep writing the words output and input all the time. So if I'm interested, notice if I'm interested in y prime tilde is g tilde of s times x prime tilde. So let's notice that I have my transfer function times x prime tilde. If this is a step function, x prime tilde gives me a 1 over s. G tilde has the denominator is all coming from the characteristic polynomial. So the important thing here is in the denominator, so I've got some sort of numerator, And here I've got the characteristic polynomial times any, if I need something coming from the input. And the input contribution, if it's a step function, it gives me a factor of s in the denominator. If it's a pulse, it gives me just a constant in the numerator, no contribution to the denominator. So most of what's going on, and remember, if it gives me a 1 over s just gives me a 0 root. And remember, the 0 roots don't do anything interesting, because when I have 1 over s, I just get a constant here. So that's not a particularly interesting, not really affecting the dynamics very much. The stability is coming from the characteristic polynomial. Any questions on that? Okay, so let's just look at a simple example. Actually, that example is silly. There's no need to look at that example. The assumption always, when I talk about numerator and denominator, is that I've canceled like factors. So I think that's so obvious I don't need to write an example where I then cancel them.
I was just going to say, I think that simple example would really help right now. There's a lot of theory happening.
I mean, okay, the thing I was going to give a simple example of is too simple. But here I can give you an example of, say, 3s plus 1 over s plus 3, s minus 2, s plus 12. If this is g tilde of s. If that's g tilde of s, and let's let x prime tilde be 5 over s, because it's a step change. So that tells me that y prime is equal to 3 is g tilde times x prime tilde is equal to 3s plus 1 divided by times 5 over s. And here I have s plus 3, s minus 2, s plus 12. And here I have an s. And this is a 5, not an s. So what's going on here? I break this up as, say, some m1, c1 over s plus 3 plus c2 over s plus s minus 2 plus c3 over s plus 12 plus c4 over s, where the c1, c2, c3, c4 depend on the numerator. So c1, for example, is equal to 3s plus 1 times 5 over s minus 2, s plus 12, s evaluated at s is equal to 3. It's similar, so it's 9, 10, 50 divided by 1 times 15 times 5. 15 times 5 is 75, is 2/3. And then, of course, I could go on following the formula for C2, C3, C4. And notice that this is going to say that y time of t is going to be equal to 2/3 e to the minus 3t plus constant C2 times e to the 2t plus C3 times e to the minus 12t plus C4. And this is a problem because whereas these two are negative, because this is s minus a minus 3, s minus a minus 12. That's why I have the minus 3 minus 12. And this is unstable because it's a positive exponential. So was that helpful?
Yeah. The one thing that's still confusing me is how you define your g your G prime, your transfer function, and then you have, I don't know, I was expecting G, because you wrote that G is equal to input over output, Y prime tilde over X prime tilde, and then you define a different X prime tilde.
Where did I define the different expression?
So 5 over S.
Oh, no, I gave an example. This is an example. You asked for an example. It's not a different one. In general, X prime tilde is whatever it is, but in this example, I'm calling it 5 over S.
Okay, but it's like, I know, I guess I'm surprised because I thought that it would appear in the original G prime function, but then.
Yeah, but once I know G prime, remember, G prime does not depend on, the reason I define out X prime is so it doesn't depend on the input. It's the result of it's the output divided by the input. So I've divided out the input. So I can switch out the inputs now. I can change, put a different X prime in. As we saw on this example over here, which of course I erased. I had an example over here for G prime, where, if you remember, at the end of the last hour, I derived G prime starting with for the step change, and I saw for the same G prime, I can swap out X prime to a pulse and get the answer for the pulse using the same G prime. So that's the whole point of G prime, is that, or G tilde, is I can swap out X prime. Once I know G, remember, we're distinguishing between the system and the disturbances. So I want G to just be system. So that way, by dividing out X prime, I get G is just system. And then I can swap out the disturbance. So G is system. And that way, once I have something that encapsulates the information of the system without the disturbances, I can put in any disturbance I like. That's the whole point of G prime. Okay? Other questions? All right, so a little bit of, let's think about G prime for G for a second. So, what do I want to say about G? I did want to say something about it. Yeah. Let's say, let's consider X prime a step. So X prime tilde is some number, I don't know, delta X over S. It's 1 over S times delta X. So let's use the final value theorem. The final value theorem says that Y prime, well, the limit as t goes to infinity of Y prime is the limit as S, well, actually, no, I want the other way around. I want to use the initial value theorem. As t goes to 0, is the limit as S goes to infinity of S Y prime tilde of S. So clearly, for a problem to make sense, the initial condition of a prime variable should be 0. So I want this to be 0 for the problem to make sense, because the initial condition of a prime variable has to be 0. So that's all if I want things to make sense. So I'm going to call so let's just, so this is the limit as S goes to infinity of S Y prime. So Y prime tilde we know is G tilde of S times X prime tilde. That's Y prime. And in this case, the limit S goes to infinity of S G prime tilde of S times X prime is delta X over S. If I want this thing to be 0, then I had better have that the limit as s goes to infinity of g tilde of s is 0. So I need the limit as s goes to infinity of g tilde of s to be 0 for the initial condition to make sense. So therefore, g tilde is, this is the definition of g tilde of s being proper. We call g tilde proper if the limit as s goes to infinity of g tilde of s is 0. Do we have a picture of this blackboard? Yeah, maybe take a picture of both blackboards. Okay, so there we define the word proper. Next thing, we're going to notice or recall that when we have a delay, f of t minus theta, t minus, what we're going to call it, t minus tau, if I have delay time, gives, when I take the Laplace transform, I get f tilde of s times e to the minus s tau. Remember that we derived. So I want you to notice that what is the delay time? Delay time means that the current value depends on what happened in the past. So the current value depended on what happened in the past. And that's something that's called causal. When the present depends on the past and not the future, past and present. Not on the future. We call it causal. Because it's not reasonable to say that what happens now depends on what's going to happen tomorrow. It can depend on what's going on now. It can depend on the changes that happen now. Can depend on what's going on now and what happened in the past, but not what's going to happen in the future. So therefore, g tilde can never have an e to the plus s tau in it, in its numerator. Because if this means the present changes depend on the past, this would mean the present changes would depend on the future. So this would not be causal. And finally, because of this, since the limit as s goes to infinity of g tilde of s must be equal to 0 if g tilde of s is a polynomial numerator, if they're both polynomials, then the highest power of s in the denominator has to be higher than the highest power of s in the numerator. And actually, that's the order. Because the order of g tilde of s is the highest power in the denominator, has to be strictly bigger than the highest power of s in numerator. So immediately, whenever you see a g, you've got a little gut check. Does g make sense? First of all, I need this to be the case. Obviously, if I have an exponential in the numerator, e to the s tau, as s goes to infinity, it's not going to go to 0. So I can't have this in the numerator. Also, if I just have polynomials, the denominator has to have a higher order than the numerator, higher power base than the numerator. Otherwise, it's not causal. It's not. I'm not going to have this. So these are sort of gut check things for G tilde. Are there any questions on it? Can I repeat what?
Just the rules about the order, the denominator.
Okay, we just discussed, we just came up with the concept of causal. And this was related to causality. This is for the problem to make any sense. So if this is going to make any sense, I need this to hold. So when would I violate this? When would I see a G that says, can't use that G, it makes no sense? If this is violated. Well, when is it violated? If the numerator has a higher power of s than the denominator, well, as s goes to infinity, the numerator wins. And I'm not going to get 0. Or if I have an exponential with a plus in the numerator, this is going to go to infinity. Those are bad. I want them to go to 0. So both of those would violate this, and we interpret this as violating causality. So it's not only just a mathematical statement, it's a nonsense statement. That's saying the changes that happen now depend on who's going to be elected in 2024 president. Well, that doesn't make any sense. What happens now depends on who was elected last year president.
So you're saying that, so the non-causal stuff is impossible?
Correct. We reject non-causal G's. We reject non-causal G's. Other questions? Okay, so I think we're ready for block diagrams. Are we ready for block diagrams? Yes, we're ready for block diagrams. Now, remember, G relates output to input for any input. G is the system. Now you might say, so far you might not appreciate why that's useful. Well, now we're going to see why they're useful. If I have a bunch of reactors or a bunch of pieces of equipment, each piece of equipment has an input and an output. If I can characterize each piece of equipment as the output for any input, how any input is turned into an output. So if so, I can hook them together any way I like and get the whole system. Okay, so what are we talking about there? Well, let's say if I have systems in series. Let's say like CSTRs. So if this is the first CSTR and I have its G, here's another CSTR, I have its G, Gn, then I know that the output from Gn, which I can call Cn, Cn is just, that's the output, that's Gn tilde times the input to this. But the input to reactor N is the output from reactor N minus 1. The output from reactor N minus 1 is Gn minus 1 tilde times its input. But its input was the output of reactor N minus 2. So immediately, I can get the overall G of the whole system in series as just the product of all the intermediate G's. And notice, I never have to write out Cn minus 1, Cn minus 2, Cn minus 3, etc. I can write Cn the output of the whole series just in terms of what comes in through the beginning. And if you remember, I had it over here, when I have two CSPRs in series, well, lo and behold, I wrote CA2 prime in terms of CAN, CAin. There's no CA1 here. I was able to eliminate it because this thing is in fact the product G1 tilde times G2 tilde. This is G1 tilde times G2 tilde. And we already spoke about the steady state gain. The steady state gain, we said, was G tilde at S is equal to 0. But that we spoke about earlier. So here's one example where I get an overall G tilde in terms of process and series. Well, we can do better than this because I want to talk about blocks. So here I can represent this as blocks. So this is reactor 1, reactor 2, reactor N. And I represent this in a block diagram this way. So here's Cn, and here's Cin. And here would be C1, C2, Cn minus 4. Well, we can do more than that. Let's look at the operations that are allowed with blocks. So block operations. So the first one is if I have a G tilde here, and I have an X tilde here, and a Y tilde here, I have that Y tilde is equal to G tilde X tilde. Well, that's nothing new. That one we knew already. That was this. I'm leaving out the prime. I should have primes. The only new thing here is not the equation, it's that I can represent this equation by this diagram, by this block. Another one, I can have a little plus sign here. So here I can have x1 prime tilde, x2 prime tilde, x3 prime tilde. So this one is, I just add. So this says x3 prime tilde is equal to x1 prime tilde plus x2 prime tilde. So I can add them. And finally, I can have a block here where I have one input, x prime tilde, and I have two outputs. Actually, I don't need a block. This is just a split. It's not a block. Sorry. It's just a split. So I take a stream and I split it into two parts. X2 prime tilde, X3 prime tilde. And you could think of this as an output stream from a reactor where I split it up into two parts. Part of it goes this way, part of it goes that way. If I'm looking at the concentration, that hasn't changed. So this tells me that x1 prime tilde equals x2 prime tilde is equal to x3 prime tilde. So here you can think where x might be concentration. If I take a stream and I split it, then the concentration doesn't change. If I take here, I might think of this, you'll see some examples where this will make sense, and this clearly makes sense.
I was just gonna, you sort of touched on it, but like, I'm confused about the second case. It's concentration within x3 is equal to x1.
I didn't say it's always the concentration. Well, in case 3, it was a concentration. In case 2, it's something different. We'll do examples. You'll see.
Okay, so it's
We'll
not
do
that
plenty.
it's any kind of variable, it really depends on what the variable is talking about.
I think the best thing is to wait until we get to the examples. So let's just notice certain things that are not allowed. So you can't have two outputs from a block. You have one output that you can then split. But you don't have two different outputs from a block. So that's not allowed. You don't have two inputs to a block. you can combine inputs first and then put them into a block, but you don't have two separate inputs into a block. I don't know how to handle those. We don't know how to handle those. And because we have these two operations, we never need to do anything like that. We can always combine them before they go in. We can always separate them once they come out. Whether that's a physical process or not doesn't matter. It's the way we represent it in a block. Finally, another one that I'm not going to allow is a multiplication term. So where the output would be the product of the inputs. Now, this is not always disallowed, but if I do that, this will be nonlinear. And we're only looking at linear processes. So why don't we do a couple of simple examples? So, let's recall what is G1 for CSTR. It's 1 over 1 plus KT, K tau, over 1 plus ST. So that was what we got for CSTR. How do I remember that? Well, remember, KP was 1 over 1 plus K tau 1 over 1 over 1 plus K tau 2. That was the two CSTRs in the series. So delta C in over S is the input prime. So this thing is G. So it's the Kp, which is 1 over 1 plus K tau 1 over 1 plus S T1. That's for the first CSTR. And for the second CSTR, I have 1 over 1 plus K tau 2 divided by 1 plus S T2. So the product of G1, G2 is this guy times this guy, which is exactly what I have here. 1 over K tau, 1 over 1 plus K tau 1 over 1 plus ST1 times 1 over K tau 2 over 1 plus ST2. Where this thing, remember, is the KP. It's C out over C in at steady state for CSTR. It's a steady state gain. And this is a steady state gain for reactor 2. Questions? Okay, so next, let's do another example. G1 tilde, G2 tilde. So here I have Y prime tilde, here I have X prime tilde. And I'd like to figure out from the G tildes, notice this is great. I can have lots of pieces of equipment. For each piece of equipment, I know the G tilde. But I would like to get the G tilde for the whole process. And that's the nice thing about block diagrams. It allows me to construct the G tilde for the whole process from the G's of the individual pieces. And it's much easier to do G for an individual piece than it is to try to do it once G for the whole process. So here I got G for the CSTRs in series in terms of the G's for each CSTR. And that agrees with the expression that we worked out last time. Let's do it here. And the way you always do this is you start from Y prime tilde and work your way back. So Y prime tilde, let's call this Y1 prime tilde, because it's the output of G1. And this we'll call Y2 prime tilde. And we can notice, because this is a plus, that Y prime tilde, this one, is equal to the sum of these two. It's just the sum. So I have Y prime tilde is equal to Y1 prime tilde plus Y2 prime tilde. And that's fine. Let's call this A, B, C. And I know that because I use B by D. But y1 prime tilde is just g1 tilde times x1 prime tilde. 2 prime tilde. And I need more space. So we're going to go up here. So that's equal to, from here, going to the next word, y prime tilde is y1 prime tilde. Y1 prime tilde is g1 tilde times x1 prime tilde. And y2 prime tilde is g2 times x2 prime tilde. And there I used A by A. And now these two were a split from x prime tilde. So I use C. By C, I note that these two have to be the same because these are all the same. So this is equal to g1 tilde plus g2 tilde times x prime tilde. So now for this system, I know that y prime tilde. Notice I eliminated all the intermediates. There are no 1s and 2s anymore. I wrote y prime tilde as g1 tilde plus g2 tilde times x prime tilde. And I used B, A, and then C. Any questions on that one? All right, let's do a little more interesting example. Let's look at you have to pull the mouse down to the rest.
I don't understand what you mean by the not allowed ones. Like,
Meaning I don't know what those diagrams mean.
like singular.
Yeah, I just don't know I don't know how to translate these into equations. So they're meaningless because I don't know how to translate them into equations. I know how to translate these. I know what equations these stand for. I don't know what equations these stand for.
Oh, okay.
In other words, these are ambiguous. You could probably write lots of different definitions for this. But this is not ambiguous. There's only one definition.
Yeah, so but now you need them, there has to be like variables with diagrams also. Right?
The diagram has to correspond to a specific equation, otherwise it's useless. Okay? Okay, let's look at this one, where this is going to be y. And obviously this is going to be x. And I need to number things. So let's number this one, say, x 0 prime tilde, x 1 prime tilde, x 2 prime tilde, x 3 prime tilde. And I want y prime tilde in terms of x prime tilde. So I'm going to need some help here. I want volunteers to help me. We start at the end, y prime tilde. And let's go back to the first operation. So here's an operation where I have x1 prime tilde is splitting up into y prime tilde and x2 prime tilde. So what do I know about the relationship between x1 prime tilde, x2 prime tilde, and y prime tilde? They're all equal. So this is equal to x prime tilde, x1 prime tilde. Right there. Okay, what's x1 prime tilde? I have a G1 tilde here. So this one was by C. What's x1 prime tilde? You have three possibilities in terms of x0 prime tilde. Somebody else? Yeah?
G1 times x0 prime.
Yes. So that's equal to G1 tilde times x0 prime tilde. Okay, now, and that was by A. Okay, so now I want them to go back to backwards to the next guy. Here I have a plus. So I know that x0 prime tilde was x3 prime tilde and x1 prime tilde contributing to it. So how do I relate x0 prime tilde to x prime tilde and x3 prime tilde? You have to use one of these. Which ones of these are you using? So B. What does B tell me?
Tells me that 3, the 0 is equal to 3 plus 1.
3 plus
Prime,
x
yeah.
prime. Yes. Good. So this was by B. So this tells me that G1 tilde, and now for x0 prime tilde, that's equal to x prime tilde plus x3 prime tilde. Okay, next. Now x3 prime tilde, how do I relate that use G2? What is x3 prime tilde? Somebody else? Yeah? You have to pull the maps down. Good. And that's by A. So I have G1 tilde times x prime tilde plus, now x3 we just said is equal to G2 times x2 prime tilde. But what did we say x2 prime tilde was? Somebody else? What is x2 prime tilde in terms of these other guys? Somebody who hasn't answered yet. What is x2 prime tilde in terms of these other guys? Yeah, okay, they're equal. So this is equal to y prime tilde. And that was because it's a split, by C. I'm doing this in gory detail. Okay, so notice now, we have y prime tilde is equal to this thing. Now I've eliminated all the 1s and 2s on the x's, 1, 2s, and 3s. But I have a y prime tilde on both sides of the equation. So I can solve that. That's not a problem. That's just algebra. So now we solve that, and we have y prime tilde is equal to G1 tilde x prime tilde plus G1 tilde G2 tilde y prime tilde. Or all I did is I distributed this. And now I bring this to the other side of the equation, factor out the y prime tilde. And I sign that y prime tilde is equal to G1 tilde over 1 minus G1 tilde G2 tilde x prime tilde. So the overall G is equal to G1 tilde over 1 minus G1 tilde G2 tilde. If I didn't have block diagrams and I had to calculate that, that would be a mess. I really wouldn't want to calculate that without the block diagrams. Now, let's see what the significance of that is. This is the overall G. First of all, when you see things like, let's look at what's going on here. Notice this is taking the output of G1, which might be a reactor, and feeding it back to the input to G1 via another reactor or another piece of equipment. This could be a distillation column, for example. I could take some of the product out and feed it back into the feed. This is my, for example, yeah. So So I have feedback loop here. When I have this kind of denominator, 1 minus a bunch of g's, is indicative of feedback. Because how did I get that? I had the y prime on the right and the left, and I had to subtract this. This was the feedback term. So that's how I got this. Now you might say, okay, lovely. That and a metric card will get me on the subway. Well, remember all this discussion we had before. I need this to be the case. My stability is based on the denominator of the overall G. When I introduce a feedback, if I didn't have feedback, I got rid of this, no feedback loop, that would be my G. So it would be the denominator of G1 that determines the stability of the system. Once I put a feedback loop in, it's no longer the denominator of G1. It's the denominator of G1 over 1 minus G1, G2. Totally different denominator, totally different stability. Well, let's see how that works out in real life. In real life, I'm not going to finish all that I wanted to finish here. In real life, in the old days is before any of us were born. Me too. Energy was cheap. Energy was cheap. So when people would design chemical plants, they would design it in such a way that if this part of the plant you need to heat up a stream, and this part of the plant you had a reaction that heated up that heated something up, you would just dump the hot stream here in some river, and you would turn on, burn some coal, and heat up the stream over here, because it's like 5 blocks apart. And energy was cheap, so it didn't matter. They didn't care if you killed some fish by heating up the stream, and coal was cheap. So what was happening was, and so the energy was not integrated. And those systems were quite stable. G1 tilde for the heat balance of that system was quite stable. All the roots had negative real parts. But energy got expensive, and we worry about the environment. So what happened probably 30 years ago, or even earlier, is that people started saying, why are we wasting money? They weren't necessarily thinking about the environment yet, but they say, why are we wasting money? Why don't we just build a pipe from here taking the hot stream, and instead of dumping it in the river, and instead of burning coal, let's put it through a heat exchanger with the stream going into a reactor over here and heat it up for free. Saves money, even if it's not a lot, it saves money. It also has the benefit of being good for the environment. Well, that's a feedback loop. Once you put a feedback loop in, and that's called heat integration, and now that's done in plants all over the place, every possible heat integration that you can do, you do for both energy savings and the environment. And now you have a new denominator, and what you find is these denominators are much less stable in heat integration. So you have to be very careful how you do it, because as they say, when a butterfly flaps its wings in Beijing, it changes the weather here in New York. Because everything is so integrated that a little disturbance, you can see why. If there's a disturbance in this part of the plant so that the stream is not as hot as it usually is, then the input stream that's being heated up by it into this reactor won't be hot enough either. So whereas a problem there stays there, the problem, what happens in Las Vegas stays in Las Vegas, it doesn't stay in Las Vegas anymore. It comes back to New York. So that's the heat integration, and that's why this is really important. Okay, So just before we finish, a couple of little coming attractions. Yeah. So what we said in the beginning of the hour is that a lot of times we can get all the information we need as opposed to all possible information, all the relevant information from the Laplace transform without inverting. Is it stable or is it going to blow up? That's what we've looked at. Is it going to oscillate or not? Well, that depends on whether the roots of the denominator are complex or real. But also, there we really concentrated on the input being either a step change, or a pulse. But as we said, sometimes you have sinusoidal inputs. Very often you have either pure sines or things that oscillate. Maybe not exactly as a sine. So you could write it as a sum of sine functions. What comes out of that? How do I learn that, understand that from Laplace transforms? Well, what are the issues? So all I'm going to get at is what the issues, the questions are, and we'll answer them next time. The question, if I have x prime tilde, and here I have y prime tilde, if x prime tilde oscillates with some frequency omega and some amplitude a, what does y prime do? Does it oscillate? If so, what is omega prime? What is the new amplitude? What is the new frequency? So if I have an input that has a certain amplitude and frequency, what is the output? Does the output oscillate? If so, what's the new amplitude? What's the new frequency? If this starts at t is equal to 0, and this oscillates, does it start oscillating immediately at t is equal to 0, or does it start oscillating at some t prime? At some t prime. That in other words, is there a lag? Is there a time lag between when this starts to oscillate and this starts to oscillate? Or if you like, are they out of phase? When this reaches its maximum, how long do you have to wait until this one reaches its maximum? So we've got 3 questions. A prime, omega prime, and phi, where phi is called the phase lag. And I'll define that explicitly next time, because it has to do with this. And all 3 of these questions are things we'll be able to answer directly from the Laplace transform, without having to do the inversion. Are there any questions? Okay, I got to get back to exams.